triangular numbers, arithmetic progressions, differences of squares and Fermat's last theorem. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. A short revision of the basic law of exponents. 1. X to the n is equal to x to the n minus 1 times x to the 1 is equal to x to the n minus 2 times x to the 2 is equal to x to the n minus 3 times x to the 3 is equal to x to the n minus 4 times x to the 4 is equal to x to the n minus 5 times x to the 5 is equal to x to the n minus 6 times x to the 6, and so that every power of x less than n is a factor of x to the n. 2. Every power of 1 to the n equals 1. The mathematician's first sleight of hand, restricting the search for a proof for Fermat's last theorem to just prime exponents, of course. Why? Well, what were the mathematical justifications for it? A fundamental basic numerical fact that has sadly been put aside by too many for too long is the following. 1. The partial sums of the cubes add to give a triangular number squared. 2. The rank of the triangular number is the same as the root of the last cube of the partial sum. And the fundamental fact? 3. As a consequence, the difference of the squares of any two adjacent triangular numbers gives the cube equal to the rank of the larger of the two numbers. Proof. 1. 9 equals 5 plus 4. 5 squared minus 4 squared equals 9. 5 squared times 9 squared minus 4 squared times 9 squared equals 9 times 9 squared equals 9 cubed. Therefore, 45 squared minus 36 squared equals 45 plus 36, all multiplied by 45 minus 36, is equal to 81 times 9 equals 729 equals 9 cubed. 2. 8 equals 4.5 plus 3.5. 4.5 squared minus 3.5 squared equals 8. 4.5 squared times 8 squared minus 3.5 squared times 8 squared is equal to 8 times 8 squared equals 8 cubed. Therefore, 36 squared minus 28 squared is equal to 36 plus 28, all multiplied by 36 minus 28, is equal to 64 times 8 equals 512 equals 8 cubed. And likewise for 7, 6 and 5. The differences of squares of the triangular numbers. What we have just demonstrated numerically is now shown graphically for the triangular numbers 1, 3, 6, 10, 15 and 21. Now it is a well established fact that the differences between adjacent squares are just the odd numbers. So we can see from the graph that all we need to do is add up all the odd numbers between any two triangular numbers to get the result for their differences. As the differences between adjacent odd numbers is constant and equal to 2, then all the odd numbers that have been added together will have formed an arithmetical progression. So between 15 and 21 we have 6 consecutive odd numbers, the first of which is 2 times 15 plus 1 equals 31, which gives us the arithmetical progression 31, 33, 35, 37, 39 and 41 equal to 216 equals 6 cubed as required. We also note that 41 equals 2 times 21 minus 1, so that both triangular numbers give us the first and last numbers in the arithmetical progression. So we can calculate the sum of the progression from the formula sum s is equal to first value plus value times the number of integers all divided by 2. So 45 squared minus 36 squared gives 2 times 36 plus 1 equals 73 as the first number in the series, and 2 times 45 minus 1 equals 89 as the last number, and 73 plus 89 all multiplied by 45 minus 36 all divided by 2 equals 729, which is 9 cubed as required. Note, 45 minus 36 can be replaced by 89 minus 73 plus 2 all divided by 2 equals 9. Arithmetical progressions for 9 squared, 9 cubed, 9 to the power 4 and 9 to the power 5. Starting with seed 9 to the power 1, we have bracket 1 plus 3 plus 5 plus 7 close bracket plus 9 plus bracket 11 plus 13 plus 15 plus 17 close bracket is equal to 4 times 18 plus 9 equals 81 equals 9 squared. Seed 9 squared. Bracket 73 plus 75 plus 77 plus 79 bracket plus 81 plus bracket 83 plus 85 plus 87 plus 89 bracket equals 4 times 162 plus 81 equals 729 equals 9 cubed. Seed 9 cubed. Bracket 721 plus 723 plus 725 plus 727 close bracket plus 729 plus bracket 731 plus 733 plus 735 plus 737 bracket equals 4 times 1458 plus 729 is equal to 6561 equals 9 to the 4th. Seed 9 to the 4th. Bracket 6553 plus 6555 plus 6557 plus 6559 close bracket plus 6561 plus bracket 6563 plus 6565 plus 6567 plus 6569 bracket equals 4 times 26,244 plus 6,561 is equal to 59,049 is equal to 9 to the power 5. Applying what we have already said in reverse, we can determine the difference of squares for the power terms from each progression. 9 cubed is equal to 89 plus 1 all divided by 2 all squared minus 73 minus 1 all divided by 2 squared is equal to 45 squared minus 36 squared is equal to 729 equals 9 cubed. 9 to the power 4 is equal to 737 plus 1 all divided by 2 squared minus 721 minus 1 all divided by 2 squared is equal to 369 squared minus 360 squared is equal to 6,561 is equal to 9 to the power 4. 9 to the power 5 is equal to 6,569 plus 1 all divided by 2 squared is equal to 6,553 minus 1 all divided by 2 squared is equal to 3,285 squared minus 3,276 squared is equal to 59,049 is equal to 9 to the power 5. The next 4 slides show exactly the same calculations shown on this slide, but for the integers 8, 7, 6 and 5. The difference of squares on slides 7 to 11 are obtained directly starting at the cube and dividing it into 2 and adding plus and minus the base number divided by 2, i.e. 729 divided by 2 is equal to 364.5 and 9 divided by 2 is equal to 4.5. 364.5 plus 4.5 equals 369 and 364.5 minus 4.5 equals 360 and 369 squared minus 360 squared is equal to 6,561 is equal to 9 to the power 4. Repeating for 9 to the power 4 gives 6,561 divided by 2 is equal to 3,280.5 and 9 over 2 equals 4.5. 3,280.5 plus 4.5 equals 3,285. 3,280.5 minus 4.5 equals 3,276 and 3,285 squared minus 3,276 squared is equal to 59,049 is equal to 9 to the power 5. So we obtain all the difference of squares for every power of every integer from the cube up to infinity by continuing the process without end ad infinitum. Alternatively, we can, by starting at the cube, increase the power in steps of 2 by repeatedly multiplying the initial differences of squares of the triangular numbers by the square of the base number, e.g. 45 squared minus 36 squared equals 9 cubed. 9 squared times 45 squared minus 9 squared times 36 squared equals 405 squared minus 324 squared is equal to 59,049 is equal to 9 to the power 5. And 9 squared times 405 squared minus 9 squared times 324 squared is equal to 3,645 squared minus 2,916 squared is equal to 4,782,969 is equal to 9 to the power 7. And 9 squared times 3,645 squared minus 9 squared times 2,916 squared is equal to 35,805 squared minus 26,344 squared is equal to 387,420,489 is equal to 9 to the power 9. And now we come to the crux of the matter, the mathematician's second and sneakiest sleight of hand, which was ignoring the cubic quadruples. The table shows two infinite series of cubic quadruples, one of which has the smallest term equal to +1, and the second series the smallest term equal to -1, and so ad infinitum. The occurrence of the cubic quadruples were dismissed as being of no mathematical relevance by considering them as just diminished or just excessive manifestations of Fermat triples, and then to merrily proceed on their fool's errand by investigating all the prime powers from 5 to infinity. Parity between odd and even integers for the triplet. For a triple, 1. Even plus even equals even, so cannot therefore replace any one term by an odd term. 2. Odd plus odd equals even, or odd plus even equals odd, as order irrelevant. 1 is not primitive, as it can be repeatedly divided by 2 until it is primitive. The three terms in 2 can be in any order, and the result is unchanged if addition is changed to subtraction. Parity between odd and even integers for the quadruple. Quadruples result from 1. A minus b equals c plus d, therefore a equals c plus d plus b, a positive quadruple. 2. A minus b equals c minus d, therefore a equals c plus b minus d, a negative quadruple. 3. A plus b equals c plus d, therefore a equals c plus d minus b, a negative quadruple. Since for the triplet we only have odd plus odd equals even, or odd plus even equals odd, then for the quadruples we can only have 4. Odd plus or minus odd equals odd plus odd, therefore odd equals odd plus odd minus or plus odd. Examples: 8703 cubed is equal to 8675 cubed plus 1851 cubed plus 1 cubed, and 163 cubed is equal to 137 cubed plus 121 cubed minus 23 cubed. All odd quadruples are less frequent than odd plus even ones. 5. Odd plus or minus evens equals odd plus evens, therefore odd equals evens plus odd minus or plus evens. Odd and even in any order, and forms the majority of cubic quadruples that I know. See table slide 14. For the fourth power we find the following quadruple due to Euler. 158 to the power 4 is equal to 134 to the power 4 plus 133 to the power 4 minus 59 to the power 4, and the associated pair 159 to the power 4 is equal to 134 to the power 4 plus 133 to the power 4 plus 1952 squared, and 159 to the power 4 is equal to 158 to the power 4 plus 59 to the power 4 plus 1952 squared, which just failed for the fourth power due to the 1952 squared term. The three quadruples result from 159 to the power 4 minus 1952 squared is equal to 158 to the power 4 plus 59 to the power 4 is equal to 134 to the power 4 plus 133 to the power 4, and this is a common feature of quadruples, including the infinite series on slide 14. 12 cubed minus 10 cubed is equal to 9 cubed minus 1 cubed is equal to 8 cubed plus 6 cubed is equal to 728. Hence 12 cubed equals 10 cubed plus 8 cubed plus 6 cubed, which being non-primitive reduces to 6 cubed equals 5 cubed plus 4 cubed plus 3 cubed to start another two infinite series. The additional two infinite series are shown in the table. We would therefore expect more positive than negative quadruples, and this is borne out by tables I have published, not necessarily comprehensive, for 975 positive and 390 negative quadruples for the same sized number field. For the fifth power, one finds the following quintuple: 144 to the power 5 equals 133 to the power 5 plus 110 to the power 5 plus 84 to the power 5 plus 27 to the power 5, and matters get worse for higher powers, so no further examples will be given. However, we can highlight the fact that a. all the higher even powers of primes of modularity 4n plus 1 will generate primitive triples and quadruples of the second power. Examples: 13 to the power 4 is equal to 156 squared plus 65 squared is equal to 120 squared plus 119 squared is equal to 169 squared, two primitive triples, which give the quadruple 156 squared is equal to 120 squared plus 119 squared minus 65 squared. B. All the higher odd powers of primes of modularity 4n plus 1 will generate mixed power triples plus square quadruples. Examples: 13 to the power 5 is equal to 598 squared plus 117 squared is equal to 597 squared plus 122 squared is equal to 507 squared plus 338 squared, and 598 squared is equal to 597 squared plus 122 squared minus 117 squared, which is equal to 507 squared plus 338 squared minus 117 squared. Several of these were known to Euler, but he didn't, as far as I know, attribute any real significance to them like I am doing so here. Summary and conclusion. There's only one number verse. 1. It has been demonstrated conclusively that for every power term their arithmetical progression equivalent and respective difference of squares terms necessary for their determination can be derived precisely starting at the cubics with the difference of squares of adjacent triangular numbers, and which can all be derived one from the other. 2. The occurrence of 4 infinite series of cubic quadruples, 2 of which just fail to be pure triples by plus or minus 1, are testament as to why pure triples of higher powers have never been found, because they are arithmetically untenable. 3. In addition, there is a profusion of pseudo-random cubic quadruples that are more than likely infinite in quantity. 4. Now, whatever level of exponentiation we look at, we are still just looking at one number field, whether it be the integer number field or the Euclidean plane, so the same self-basic laws of arithmetic apply irrespective of the size of exponent. This is confirmed by the occurrence of either mixed power triples, primitive all-square triples, or all-square quadruples at all levels of exponentiation, whether odd or even, and in quantities of infinite extent. These are due solely to the fact that all primes of modularity 4n+1 are the sum of two squares, which is the selfsame reason that Pythagorean triples exist. 5. Since the seed for the arithmetic progressions of the integers I to the power 0 equals 1 applies, then all integers are given by 1 plus 1 plus 1 plus 1 plus 1 and so on and so forth for as many ones as are equal to the value of the integer. 6. We note that the compact arithmetic progressions for the squares also start with a 1, and that both the powers 1 and 2 form integer triples with all three terms of that power. It is also a fact that the integer and square sequences both have a linear rate of change, whilst all higher powers have ever increasing exponential rates of change, alias divergence. 7. It has been demonstrated for both the Pythagorean triples and the cubic quadruples that the respective parity between the odd and even integers must exist in order for triples or quadruples to form. The repeating footprint for the arithmetical progressions shows that the parity necessary for the existence of a Fermat triple is destroyed by divergence, reductio ad absurdum, QED.